So yeah, I've been working with Python since 1.5, I believe. That's when I first got into it. I actually worked with Tim Peters at Dragon Systems in Massachusetts. If you know who Tim is, you've probably seen some of the things he's written. And today I'm going to talk about REST service load testing. So for this company I'm working with, we have a cloud service running in Azure. It's actually running Mattermost server, a chat server written in Go. And our customer wanted to know how well it would perform under load. So I'm like, okay, well, I think it would do fine. I mean, but they wanted some actual numbers. So I thought, well, I could look into some tools, see what's out there. But I'm like, well, this can't be that hard to do. And I hadn't done any async IO stuff. I hadn't actually really done too much Python 3 programming. Still stuck in the 2.7 world. But I gave it a shot, and it came out pretty well. And I'm going to talk about some of the features that I used. I'm going to show code, but it shouldn't be too complicated. And I hope it actually illustrates how simple it can be to use the 3.5, 3.6 async IO capabilities. So for testing, what are we trying to do? So we're going to try to simulate multiple users using this live chat cloud service. We're going to be performing a variety of GET and POST transactions over HTTPS. And all of these users are on their own. You know, they should be just as if we had people coming in and using the service. We don't want to be blocked, so we want to do as much concurrent processing as possible. And I'll talk about this in a little bit, but later in the talk. But we don't want to just, lockstep send out a request every, say, 0.5 seconds. We actually want to see how the system will perform as users come on and they start logging in. So this is kind of what's called a random, a stochastic random process, a Poisson process. And of course, we want to record the times that it takes to actually do these activities. So real quick, here's what we're going to be doing. We're going to be logging in. We're going to be fetching some stuff. This is all based on what Mattermost offers and what the client wanted for their users. So there's quite a bit of stuff that we're going to be doing. I'm not going to go through all of these. I'm just going to illustrate some common principles that we use to get these things to work. Now, the fundamental building blocks that we're using are it is 3.5 at least, because we want to use the async and the await expressions in Python code. We're using the async IO module, because that gives us a run loop, although you could use another run loop as well if you wanted. And I'm relying on the AIO HTTP module that's separate from the Python base. And that gives us all the HTTP connectivity stuff, and it's all highly performant, and it's using asynchronous processing. Finally, there's actually a bit that I will show you I'm still using the multiprocessing library of Python. And the reason is that even though with asynchronous processing, we gain some concurrency, we are still, using one event loop. And if we have multiple users acting independently, that can cause some blockage. So we want to have all our users operating independently. We'll use multiprocessing to do that. Now, this is a really noisy slide, but basically it's just showing, for those who don't quite understand what async IO does, you start with an event loop, and in this event loop you have these tasks, and tasks can have one or more essentially futures or coroutines associated with them, and they will not make any further progress until the coroutine that they're dependent on finishes and gives them a response back or an error out. And so that's just basically what this is illustrating, that we can always make progress even if something else is waiting. That's the gist of async IO. Now into some code. So first we're going to set up, I have by By the way, this is only about 250 lines of code. It's in one file that does all of this processing. So it's very simple, although it may look a little odd. But anyway, I have a class called Mattermost that's going to be the test driver. It knows how to talk to the Mattermost server, and it's going to be issuing these requests and look at the responses. Again, I'm introducing a run loop. This is from the async IO. And this client session here is actually from AIO HTTP, which provides me connection pooling. And again, it also knows how to do all the HTTP arbitration. Now, I need to do a login. That's the first thing I'm going to have to do as a user. And here we have a method in our Mattermost class that's tagged as async. So right off the bat, we have something new in Python. It's this, Python 3.5 and later. And it's basically saying that this method here, login, will return when you call it, but you actually don't know it's not going to do anything yet. It's going to wait until it gets into the event loop and look at what's inside and say, oh, I've got some more things to do. I can either, I need to wait for something to finish processing, or I can return to the caller. And I'll show you how that happens. But that's the first thing. We have this async tag. And within it, we actually have another async. We're saying, OK, we're going to set up the attributes for our REST call. And it's a post transaction. So I have a URL and all the stuff that I'm handing to the call. And I'm going to wait for that to happen. I'm going to wait for the response. So I can't make any further progress until that comes back. However, the rest of the code can do whatever it wants. The event loop is still running. Once I get a response back from the post transaction, I interrogate it to see if it succeeded or not. And then I also await here on the response, because maybe it's going to take a long time to do the processing of the payload. It doesn't take too long here. And then finally, I return the results to the caller. But I'm not actually returning the results to the caller at the time that it was invoked, and this is what we're going to talk about here. So now I've been my driver. So I've got the Mattermost server, or the Mattermost class that knows how to talk to the Mattermost cloud instance. But now I got the code that's actually going to execute the tests. And it's going to be invoking all these different methods. And here we have to keep track of what these methods are, because we're not going to get the results immediately. So I'm in queuing, and on the next slide, I'll talk about these methods there. But basically, I'm saying, OK, I want to run the login method. I'm going to give it the parameters, because these are all going to change based on the user that I'm running under. And when that's done, I can't make any further progress in my script until I get the login back. Just nothing else will work until I get an auth token. So the next line here says, OK, I'm going to wait until it's done. So here we go with those two methods. On the in-queue side, I'm just basically adding a future to an array. I'm just remembering that I've got something in flight, and I'm going to have to check back later to see what the result is. When I'm ready to check, I execute done. And now I'm asking the run loop to say, hey, don't continue on until all the stuff that's in the tasks array is complete, or it errored out or whatever. And so that's the async IO wait there. Finally, I'm grabbing the results and returning them back to the caller in the invocation step. And a GET request is much the same. I'm not going to go here, but it's just there's a GET verb, just like there's a POST verb. Now I can execute these things in parallel. These are independent requests, and so there's no tying of these requests together. I can say, oh, I need to fetch the roster of the people who are in the chat, who's in the chat, and fetch the posts that is in the chat, the latest posts. Those can happen independently, and I'm also creating a WebSocket, and I'm doing that in a little bit different way because of the way I'm finishing the test. So now I have a way of sending requests to my server, getting the responses back, going back and forth, going all the way through, getting everything there, Finally, I send a message because I want to test round trip time. I want to test logging in, getting all the updates, and then sending a message and seeing that message come back over the WebSocket. That's my definition of the test. Because that'll give me a good idea of how much time it takes to actually do all those steps. Now, as I mentioned earlier, I don't want each of our users, or these simulated users, to interfere with one another. So I'm spawning them. I'm using multiprocessing to basically run the run method as a separate process. I keep them all synced up, and I let them go on their way. Now that I've got all these processes running, they're going to do their thing, I need to actually collect the results. Or as in a map reduce, I'm doing the reduce step. So now I'm bringing back all the results together from these separate processes, and I'm generating a file. So this is just noise, but the p.join there is the actual multiprocessing, or the process method that is blocking until the process has returned. And here's a really not very clear slide, but I throw the data into IPython, and with pandas I can read it and see the elapsed times and the different stages, the overall time, which is off the screen. So that's pretty good. Well, real quick. The first column, or the third column here actually, is delay. And as I mentioned earlier, I don't want just users like every 1 second, every 2 seconds to come in and do a request. I actually want them just to be kind of random, but I want to be able to control the rate. I don't want them all to appear, so there's got to be some way I can specify that I would like some rate of users to appear and do some things on the server, while at the same time not keeping them lockstep. And that's what the Poisson process is. So again, we want a distribution of these intervals between when a user comes in. It's a completely random, that interval value. But we want on average that interval to be some value that we understand. So here's a hypothetical model. We have 10,000 users, and we want to run this simulation over 2 hours. That gives us a rate of 1.3, 1.4 users per second coming at our server and doing stuff. Or you can invert that and you get basically an interval of 0.7 seconds between users coming in. And that's, again, an average spacing. This is not guaranteed. It's not what you would see in the real world. So what can we do? Well, with a Poisson process, you basically you start with nothing happening, and as time progresses, the probability increases, the cumulative probability increases of an event actually taking place. It actually never goes to absolute to 1, but because there's always a chance of something else not happening, that's always a possibility. So you just keep waiting, you keep waiting, you keep waiting, and you can, using that interval, what you're expected to see, which is this 0.72, you can, basically you would see a distribution, a normal distribution of your intervals laid out, centered around this 0.72 for very large numbers. And then, but each of the actual deltas would be all over the place, essentially. So on average, we expect to see 0.72 if we do a large sample. However, we can see users coming in almost simultaneously. We can see them spread out quite a bit, because those are non-zero probabilities. And so maybe this is a good thing to do, to say, well, geez, even though we, over historically, historical data, we've said, oh, we only see people coming in at 1.3 users a second. Well, maybe what happens when they all come in, when they wake up in the morning and they check our servers? And so maybe that's what we really should be looking at, rather than just say, oh, over average is 1.3. So how do we do those times I showed in that column a couple slides ago? Well, again, with it's an exponential. Poisson process has an exponential distribution for the times. And you can generate them using a log function together with a probability, a random value of 0 to 1. And this is taken from an IPython document that I'd created. And here's the only time I actually show is some NumPy, but it shows you how you could actually generate these values. And here I'm generating 1 to the 6th values, and I actually get the almost 0.72 response that I expect. So it looks pretty good. Now I have all these random deltas. How do I get to the times? Well, again, those are actually basically just add them up. So if I'm number 5 user in my simulation, and I'm going to run 100 users, and I have number 5, the easiest thing to do is he will start doing his thing at the time, which is the sum of the first 4 deltas that we calculated. And so you can just generate a running sum here in Python, or it's much easier to do in NumPy. Now, just to show you what those deltas look like, here's a plot of them. And you can see that overall, most of the stuff is below 1, which we would expect because of the point we saw over a large number of deltas. We should get about 0.72. So below 1 should be a majority of our deltas. But we do see, periodically some large gaps. All right. And we also have quite a bit of stuff way below 0.72. So here's some real-world measurements that I'd done for a customer. And it's hard to see on the side, but there's actually a decimal point. So for this was 100 users over 20 seconds. And the worst case was, some 3-second delay doing all that work. That was pretty nice. It was not too bad. They were happy with that. And we break it down into the actual individual steps, so we could see if there's any hotspots that perhaps we could do some caching to get rid of. Okay, let's look at 100 users over 10 seconds. Now we see now here we've gone to some the spike here is at over 6 seconds it took for a user to actually do all that work. Which is not so good, but it actually didn't do so well overall. So maybe it's not so bad. And it still performed, it stood up, which is pretty nice to know. So that's basically it for my talk. There's additional information of the code. Like I said, is 250 lines. It's in GitHub at this address. My blog, Keystroke Countdown, has some additional information. It has the IPython pages that I clipped out in the presentation. And additional documentation is listed here. Finally, an excellent resource is the High Performance Python book, O'Reilly book. I highly recommend it. They do a really good job of explaining various reasons why you would go one way or the other in the async space. Really good. Any questions? Yeah. Oh, and I apologize if I talk too fast. And I'm a native English speaker.
How would you compare multiprocessing and async I/O?
Pardon me?
Well, I understand that multiprocessing is simpler if you don't have shared data. And you have no problems with overhead of creating process.
Yes.
So I usually use multiprocessing. So, except these 2 cases, when would you recommend me to use async I/O?
Well, I think you basically said it, right? So, so you're still with async I/O. You still have the guild to contend with. You still have, you're not just free will, just throwing a whole bunch of stuff out there. And a lot of stuff is not in Python libraries. They're still migrating over to asynchronous implementations. So if like I basically know that AIO HTTP was going to be a very good high-performant means of executing HTTP transactions and getting high, high concurrency. So there, and since most of the, if you saw some of these requests take half a second, maybe up to a second. So during that time, the interpreter is fine to do whatever else it wants to do. So I think definitely in the networking space, async IO wins big time. Now, understanding the whole, the async and the await stuff and what can you use, whether it's a futures or a generator or iterator, it makes me, gets me confused. I'm not used to it. So there was a steep learning curve from my point of view. But I think it was worth it. Now, I've done a lot of multiprocessing stuff, and it's the marshaling of the data between the processes that is the hardest to get right. And then once something fails, it all falls down, and it's hard to get everything restarted correctly, and because you have zombie processes sometimes hanging out. But it works. I think that since my requests in that whole list of requests, they were dependent upon the data that came back. So I had steps that I couldn't make forward progress until I got a response. In that case, I think it made sense to do the async IO. Doing multiprocessing, I'm just going to spin up a whole bunch of processes, and then I have to do the whole marshaling around of the intermediate data to make any further progress. And then I'm also incurring the latencies going over the net, doing that kind of stuff. So definitely for this kind of measurement, I think async IO is a big winner.
Thank you.
I'd like to ask you which libraries you have for plotting the data. Like you show the graphs. You have some nice.
Matplotlib.
Yeah. Okay.
Yeah, it was part of IPython, so it works pretty well. But it's like, it's actually you could tweak it, all right, but so what you see on the web is much better than what you got here because of the loss of detail. And plus, I was basically cutting images. So.
Okay, thank you.
Thanks. Okay, how would you test an application that has WebSockets and REST as well, but they're dependent from each other? For example, you create a user does an action, and something is thrown to a WebSocket. I want to test the delta in between, those things which are completely different. I don't know if I made myself clear.
No, yeah, sure. So yeah, I did not talk about the WebSocket other than I alluded to that I am actually using a WebSocket. And at one part, after I've gotten the authentication, I know some other information, I can finally start a WebSocket. Parts of code that I did not show is actually the termination step for my test. And so I'm doing all the setup, I'm getting all the data from the server, and my final measurement is to do a HTTP post, send a new message to the server. And I've already stood up this WebSocket, and the WebSocket will receive that new notification. That's how Mattermost conveys or keeps people, happy in real time using WebSocket. And there's support in the WebSocket protocol, or the implementation I'm using, and I can't remember right now if it's a separate piece of code or it's the part of AIO HTTP. But I'm basically waiting, using async stuff, to see what data comes back over that WebSocket. I ignore some stuff because when I'm logging in, I actually see myself logging in and being part of that channel. And so when I send that message, all I'm doing is just waiting in a future until I see my own message come back. And I've got the round trip. And so you can easily do that with async IO. And again, I'm not sure, in the slides on the last one, there's a link to GitHub gist that actually you can see the code that uses the WebSocket stuff.
I think you could show the slide.
Yeah, let me, or I can, do we actually post the slides? Yeah.
Right, do we have any more questions? Looks like no. So thank you.
All right, thank you.